Today we're going to learn about transformations of linear functions. And transformations are when you take a graph and you change its size, its shape, its position, or its orientation. So there are four main types of transformation that we'll look at today. The first one is translation. It's when you take a graph and you just shift it to the left or the right, or shift it up or down. A reflection is when you do a mirror image of the graph. It's a transformation that flips a graph over some sort of line of reflection. And the ones that we're going to learn about first are over the x-axis or the y-axis. Next type is a horizontal stretch, where we take a graph and we stretch it out or compress it down, either vertically or horizontally. And so horizontal stretch would be horizontally, and vertical stretch would be vertically. And so we're going to look at each of those types of functions in turn, or each of those types of transformations in turn. It's important to realize that the most basic function is called the parent function. So because we're focusing on linear equations in this section, the parent function is f of x equals x. This is the simplest linear equation that we can come up with for a non-constant linear function. And then a family of functions would be all of those related functions that are based off of the one parent function. Let's start with translations first. So here you can kind of visually see what's happening to my original black line here. The black line can be shifted up to create this blue line, or shifted down to create this red line. Now, linear transformations can be hard to visualize because lines have no unique features that you can track. So what I've done is I put an X on each of these lines so you can follow one point and see what happens to that one point as the translation occurs. So here you can see that the X has been shifted up or down in this vertical translation. In a horizontal translation, you can see that the X has been moved to the left, or in the case of the red line, or to the right in the case of the blue line. Now, one thing that you're going to notice again and again as we go through this is that some of our transformations occur to the output value. The change happens after you've already calculated the function, the value of the function. Other transformations occur to the input value before you even plug it into the equation. And we're going to see a pattern in how we handle those transformations. So let's start with an example here with these translations, and we'll see how they work. So this function, f of x equals 2x minus 1, is graphed here. You can see that y-intercept is at -1, and we have a slope of 2. And now we're trying to draw two new versions of this line. One of them is g of x, and one of them is t of x. And each of these takes that f of x function and makes a slight change to it. In the first case, for g of x, we evaluate the function, and then after we've evaluated the function, we add 3 to the value. And so this is one of those cases where we our change is to the output value, because we evaluate the regular function and then we do something to it. For t of x, notice we take the function of x plus 3. We're changing the input value here. So that's the difference in these two transformations. Both of these add 3 at some point in the function, but they add it at different places. For example, the g example, we're affecting the output value. For the t example, we're affecting the input value. For now, I'm going to focus on g of x, and then we'll look at t of x later. Here are a couple of values that you see on the graph. At 0, the graph is -1. The y value is -1. And at 1 is up here, the value is 1 in the y direction. So here I've marked off kind of 2 points that are on the line already. But now I want to graph g of x. So what I'm going to do is I'm going to basically evaluate f of x and just add 3 onto what I had in the first place. So I'm doing f of x plus 3. That basically means I'm doing the 2x minus 1 and that I'm adding 3 to it. So in a sense, essentially I'm doing 2x plus 2. So if I plug in 0 for my x value, 2 times 0 is 0 and add 2 and I get 2. When I plug in the 1, 2 times 1 is 2 and add 2, I get 4. Notice I could have achieved the same thing by just taking this value and adding 3 to it. Taking this value and adding 3 to it. Because that's what the g function is telling me to do. Calculate the original f function and add 3 to it. So where I previously had a point at 0, negative 1, that point is now at 0, 2. Oh, I can't count. It's at 0, 2. And where I previously had a point at 1, 1, that point is now at 1, 4. So my new line is parallel to my old line. It still has a slope of 2. I'll do my best to draw a good line here. But in this case, I'm shifted up 3 units. This is a shift up of 3 units. Let's look at what happens when we change the input value. We change the input value before we even evaluate the function. Here you can see I'm using different x values. I chose these x values carefully and you'll see why in a moment. So what we're doing here is we're doing f of x plus 3. So we're going to do 2 times x plus 3 and then subtract 1. So when I plug in a negative 3 for x, negative 3 plus 3 is 0, times 2 is still 0, and then I subtract 1. When I plug in negative 2 for x, negative 2 plus 3 is 5. Multiplied by, I'm sorry, negative 2 plus 3 is 1. Multiply by 2 is 2, and I subtract 1, and that gives me an answer of 1. The reason I chose these values is notice my output values are the exact same as my original function, but I chose different input values. I chose different input values. In fact, I'm going to do this all in purple, just so that you can tell the difference between these lines. So what I have now when I draw this graph is I have a point at negative 3, negative 1. 1, 2, 3, negative 1. I have a point here. And I have a point at negative 2, positive 1. So these original points on my original graph, you can see that this is now a shift to the left. A shift to the left. If I go ahead and plot a few more points here so that I can hopefully draw a reasonably straight line. Okay, you see that I have a shift to the left of 1, 2, 3 units. Now, here, when we added 3, the shift was upward. And for the g function, the shift was upward. It was in the y direction, and the shift was in the direction we expect. Positive means up, negative means down. In general, when you deal with transformations that affect the output value. The transformations are what you expect. And I'm going to scroll up a little bit so we can see this here. Transformations that affect the output value applied after evaluating the original function occur in the y direction and have the effect that you expect. Transformations that affect the input value, you apply the change before evaluating the original function, occur in the x direction and have an effect opposite to what's expected. What I mean by that is here we added 3. You might expect that to mean a shift in the positive direction for x, a shift to the right. However, this is the opposite of what's expected because we have to basically, to get back to the original input value of 0, we have to start at -3 so that we can add 3 to get to 0. So it's like we have to do the opposite to get back to the original place where we started. We have to subtract 3 to get back to the original place we started. So transformations that affect input values tend to have the backwards effect to what you're expecting. In this case, a shift to the left, even though it's a +3 transformation. Let's look at reflections now. Again, with reflections, you can have a change to the function after you have evaluated the original function, or you can have a change that occurs to x before you evaluate the function. So let's look at examples of these. Here, when we reflect across the x-axis, we are changing the outputs. We are multiplying the outputs by -1 to change their signs. On the other hand, when we change the input values, when we multiply the input values by -1, that causes a reflection across the y-axis. Again, watch the x's because the two graphs looks very similar, but look at what's happening to the x's, where the x's changed locations to really spot what the change in the graph is. Notice that when you flip across the x-axis, the x-intercept does not change. The x-intercept stays frozen. Similarly, when you reflect across the y-axis, the y-intercept remains frozen, stays the same for the original equation and the reflected equation. So let's look at some examples and how to figure those out. If we start with the original function, f of x equals 1/2 x plus 1, we've got the graph here with a y-intercept at 1 and a slope of 1/2. That means for every 1 we go up, we go to the right 2. And for g of x, we're going to evaluate f of x and then multiply by -1. So here we are affecting the output values. In contrast, when we do the second example, we're going to do t of x equals f of -x. Here we're changing the input value. And so one of these is going to be a reflection in the x-axis and one is going to be a reflection in the y-axis. So let me scroll down so we can see a data table here. If we start with the point -4, the y value is -1. When the x value is -2, the y value is 0. And when the x value is 0, the y value is 1. So we've plotted 3 points on this original line. And that's going to help us compare when we plot a few points on the g function here. I'm going to do everything that I did for the original version of the equation, of the original function, but I'm going to multiply by my answer by -1. So with an input of 4, my output value is now going to be +1. With an input of -2, my output is going to be -0. Well, -1 times 0 is just 0. And with an input of 0, my output value is not going to be 1, it's going to be -1. So I've just taken all of these values and multiplied by -1. Multiplied by -1. Plotting those points on the graph, I now have points at -4, -4, 1, which is up here, -2, 0, so those points overlap, and 0, -1. So I can continue this pattern as just to give myself a few more dots to hopefully draw a straight line off of. And now I'll try to draw this reasonably. And you can see that I have a reflection across the x-axis, and I can tell it's a reflection across the x-axis because my x-intercept stayed the same. Now let's look at a reflection across the y-axis. We've already said that the t of x function affects the input values. If you notice here, I changed my values of x from before, but I changed them in a very careful way. Notice that I took my original -4 and I changed it to 4. I took my original -2 and changed it to 2. I took my 0 and that stayed as 0 because 0 times -1 is 0. Now I take those values 4, 2, and 0 and plug them into the equation. But notice I do 1/2 times -4, which is -2, plus 1 is -1. 2, plug it into the equation, I have -2 times 1/2 is -1, plus 1 is 0. And if I plug 0 into the equation, 0 times 1/2 is 0, plus 1 is +1. Notice that I chose my x values very carefully to show that I needed to flip the sign on my input values, get those same values back. So if I plot now, when I'm over here at 4, my point is at -1. When I'm at 2, my point is at 0. And when I'm at 0, my point is at +1. So this y-intercept point overlaps. And if I draw a few more points to extend this, just to help me draw a straighter line, then my line looks like this. And notice that this is a reflection across the y-axis because the y-intercept stayed the same. So, in summary of what these changes are, the function g was a reflection across the x-axis. And we can tell that because the x-intercept is not changed. It's unchanged. And for t of x, this t function, this was a reflection across the y-axis. And we can tell that because the y-intercept was not changed. So that shows you an example of what a reflection in the x-axis looks like and what a reflection across the y-axis looks like. Now let's look at vertical stretches and vertical shrinks, and then we'll look at horizontal stretches and horizontal shrinks. Vertical stretches and vertical shrinks happen in the y direction. They affect the this change is in the output values of the function, okay? The x-intercept is going to stay the same in a vertical stretch or a vertical shrink. And this is what a vertical stretch or shrink looks like. A vertical stretch here is represented by the blue line. Because just imagine that you've got silly putty or taffy and you're drawing the line, the original black line vertically. And then a vertical shrink is when you compress in the y direction. And that's represented by the red line here, where we've kind of flattened in the y direction. To stretch in the y direction, you have a value, a multiplication factor here, which is represented by a. And your a is bigger than 1 to cause a stretch in the y direction. And if a is less than 1, but still greater than 0, then you have a shrink in the vertical direction. Of course, if a is negative, then you've done a reflection across the x-axis. In contrast, horizontal stretches and horizontal shrinks occur in the x direction. And maybe you've spotted the pattern by now. This affects the input values. So the change is perhaps opposite of what you're expecting given the changes we saw in the y direction. So with a horizontal stretch is a stretch in the horizontal direction, outward, side to side. But to achieve that, your multiplication factor is going to be less than 1, greater than 0, but less than 1, which is perhaps the opposite of what you're expecting. This is because we're affecting the input values, not the output values. On the other hand, if you want a horizontal shrink, if you want to compress in the horizontal direction, you are going to use a multiplication factor that's greater than 1. So once again, in a horizontal stretch and shrink, we are affecting the input values. And with a vertical stretch or vertical shrink, we're affecting the output values. So let's do a couple of examples of these. Here I have the graph of f of x equals x minus 1. So my y-intercept is here at -1, and my slope is just +1. And here I have h of x equals 3 f of x. Notice that my multiplication happens after I evaluate f of x. So here I'm affecting the output values. I cannot spell output values. Okay, so my original function has points at 0, -1, which I've already marked, 1, 0, and 3, 2. So those are 3 points on my original graph. Because this multiplication factor affects my output values, this should be a vertical stretch or shrink. And because this 3 is bigger than 1, this is going to be a vertical stretch. So this will be a vertical stretch by a factor of 3. So let's see what that looks like. H of x equals 3 times f of x, and the original f of x was x minus 1. So if I plug 0 in here, I get -3 as my value. If I plug 1 in here, I get 0 as my value. And if I plug 3 in, I get 6 as my value. Notice that each of those values are 3 times the original x value, because that's the transformation we did. We are multiplying the output value times 3. All right, so let's plot those points. At 0, I have a value of -3. Right here. At 1, I have the point 0, so that duplicates that point that I have there. And then at 3, I have a value of 6, which is actually slightly off the graph here. And if I connect those points, I can draw one more point in here. If I connect the dots, I end up with a stretch, a vertical stretch that looks like that. This is my F graph. I'm sorry, this is my H graph here. My H graph here. Notice that the x-intercept is unchanged. The x-intercept is unchanged. That's one of the features of a vertical stretch. That's how you can tell it's a vertical stretch, not a horizontal stretch. All right. Let's look at this example, the g function. Once again, I'm using different values of x here, but I chose those values carefully. Here, my function is of, my input values are being changed. Notice I'm inputting, my input values are going to be cut by a third, multiplied by a third. And so to get the original y values that I had from my original function, I'm going to have to start with a number 3 times as big as what I usually have, or what I had before. So instead of starting with 0, well, 3 times 0 is just 0. But instead of starting with 1, I'm going to start with 3 times that much. I'm going to start with 3. Instead of starting with 3, I'm going to start with 3 times that much. I'm going to start with 9. So when I plug those values, 0, 3, and 9, into the original equation, 0 times a third is 0, minus 1 is negative 1. 3 times a third is 1, and then I minus 1, and that's 0. 9 times a third is 3, minus 1 is 2. So notice I've got the same output values as before, but I had to manipulate my input values to get those same values. If I plot these points on the graph, I get points at 0, negative 1. So notice that point overlaps. 3, 0 is a point on the graph. 1, 2, 3, 0. And 9, 2 is a point on the graph. So if I graph this carefully, I will get a line that looks like this. And this graph of the g function is a horizontal stretch by a factor of 3. I cannot spell. Stretch by a factor of 3. Now look at that. There's a 1/3 in the function, but the horizontal stretch is by 3. Why is it by 3? Look at what I had to do to my input values to get the original output values. I had to make the input values 3 times as big to get those output values. So once again, we see that the change for the x direction, the change when we are talking about x transformations is the opposite of what you might expect. The horizontal stretch is times 3, which is the inverse of that fraction there. Instead of being 1/3, you do the reciprocal and you get 3/1, which is 3. Notice for this horizontal stretch that the y-intercept is unchanged. And that is how we can tell that this was a horizontal stretch as opposed to a vertical shrink, because that y-intercept is unchanged. We've now done 2 different stretches. Let's do some shrinks now and see what those look like. So if our original function is it looks like my f disappeared. If f of x equals x plus 2, notice my intercept is at 2 and my slope is 1. And then I'm going to transform that by evaluating k of x here. K of x, I want to do this in red. I'm taking my original f of x function, but multiplying it by a factor after I've done the function. So here I'm affecting my output values. And this is going to result in a vertical shrink. A vertical shrink by a factor of 1/4. A vertical shrink by a factor of 1/4. Remember, when the change happens to the output value, then the change is what you expect. You don't have to make it the opposite or anything like that. We multiplied by 1/4 at the end of the function, so the shrink is by a factor of 1/4. So we're going to take, if we plot these original 3 points on our original function, -4 gives us a value of -2. -2 is the input, gives us a 0 output, and 0 input gives us +2 output. So there are the 3 points that we just graphed. And now I'm going to transform this function to k, the k function, by multiplying each of these output values by 1/4. So -2 times 1/4 is -1/2. 0 times 1/4 is 0. 2 times 1/4 is +1/2. Of course, I could take the original x values and plug them into the equation, but because this 1/4 is being applied to the function afterwards, I've already evaluated the function, so I'm just saving myself time by multiplying by the 1/4 after evaluating the function. Let's plot those points now. I have a point at -4, -1/2. So that's here. I have a point at -2 and 0. So this point stays the same. And then I have a point at 0, +1/2. So this is a very shallow line. And I go basically up half a unit and over 2 units. So I'm going to go up 1 and over 4, up 1 over 4, and I can go down 1. Actually, let me do this here. I'll go down 1 over 4. So if I connect those dots as best I can, this is the graph of k. And notice that the x-intercept does stay unchanged. The x-intercept is unchanged. Once again, that's how I'm sure that I have done a vertical shrink as opposed to a horizontal stretch. Remember up here, my horizontal stretch is in purple, this G figure here, but that G transformation had the same y-intercept. That's how I knew it was a horizontal stretch, not a vertical shrink, which has the same x-intercept. Let's look at this J function now. For this J function, notice that the change happens to the input value. I've changed my input value, which means this is going to be some sort of horizontal change. And because horizontal changes in the x direction are always the opposite of what I think, this is going to be a horizontal shrink by a factor not of 2, but by a factor, I'm going to flip the fraction again, but by a factor of 1/2. So I'm going to have a horizontal shrink by a factor of 1/2. So let's see how this looks. Notice that in order to do a good comparison, I've chosen my x values carefully. Before, I started with a value of -4, but now I'm starting with a value half that big because I'm going to multiply it by 2. And so if I do -2 times 2, that gets me back to -4. So I have to do the opposite of what the function seems to be telling me to do. So when I plug the -2 into the equation, -2 times 2 is -4. Add the 2, that gives me -2. -2 times -1 is -2. Add 2 is 0. 0 times 2 is 0. Add 2 is 2. So notice that my y values do exactly match up with the original function. When I plot the graph, I have points at -2, -2. I have a point at -1, 0. And I have a point at 0, +2. So that overlaps with what it was before. I'll just draw a couple more points here to make drawing my line easier. And then I'll draw in this horizontal shrink. I'll label it with the letter J. And that shows me a horizontal shrinking of the line by a factor of 1/2. Notice that the y-intercept is unchanged from the original function f. How do we put this all together? So far, we've focused on one function at a time. What if, and one change at a time? What if there are multiple changes? Well, to combine transformations, if you think about your multiplication factor, if you think about any subtraction you do to the original input value, and any addition you do after evaluating the function. Here we still have a multiplication factor, subtraction that we do to the input value, or any addition that we do to the output value. We're going to talk about each of these steps and which ones you do first, which ones you do second, which ones you do third, what kind of order to apply each transformation is. So, step 1. Before I go through the steps, let's look at the problem we're going to do. F of x equals x is graphed, and that is down here a bit. There we go. You can see that the y-intercept is 0 and the slope is +1. This is the most basic parent function, f of x equals x. We're going to transform this in a couple ways. We want to graph g of x equals -2x plus 3. So notice I've got a multiplication factor on the x, and I'm adding 3 to it. We need to describe the transformations that we're going to take to get from the graph of f to the graph of g. So first, we want to make sure that we can rewrite g of x in terms of f of x. We want to be really clear about what transformations are affecting the input value and what transformations are affecting the output value. So, first of all, that -2x, that doesn't seem to apply to the whole equation. There are a couple different ways to write this. This is why linear equations are so tricky. I'll just write this in red. I'm going to rewrite this as g of x equals, let's see, this right here is my f of x. F of x equals x. So if I just kind of replace that x with f of x and write it that way. So -2 times f of x plus 3. Okay. So so that was my step 0. I rewrote my transformed function in terms of the original function. So I wanted to be sure that my f of x was written in that function. So now I can see, hey, what addition or subtraction or multiplication is there to transform this function. Step 1, if there's any horizontal translation, if there's an h value that I'm adding or subtracting from x before I evaluate the function, I do that first. You do any input additions first. Well, notice here there's no change to the input value. My input value is still x. Therefore, in this example, there is no h value. So there is no horizontal translation. Nor horizontal translation because there's nothing being added to the x. If my equation looked like -2 times f of x plus 3, that would require a horizontal translation. All right. Step 2. Use the absolute value of a, and remember a is this multiplication factor. It doesn't matter if it's inside the parentheses or outside the parentheses. So I'm treating it like it's outside the parentheses. That multiplication factor to stretch or shrink the resulting graph. Here, my multiplication factor is 2. I'm just focusing on the absolute value right now. So I'm going to ignore the negative sign for right now. We'll deal with the negative in a later step. But my multiplication factor is 2, and it happens to the output value. I evaluate f of x first, and then I multiply by 2, or -2. So there is going to be a vertical stretch, not horizontal. Horizontal would be to the input value. This is to the output value. A vertical stretch by a factor of 2. So I'm going to come to my graph here, and I'm going to apply a vertical stretch by a factor of 2. I'm going to go in this direction. Where I had 1, I now have 2. Where I have -1, I have got negative 2. Where I've got -2, I now have -4. And that's what my vertical stretch looks like. So this is my graph, not of my final g function, but just of step 2. I stretched it, and now I have this graph. Step 3, I'm going to do this in a different color. Step 3, if a is negative, reflect the resulting graph across the x-axis. Okay, so a is negative, my multiplication factor is negative, so I need to transform this by doing a reflection across the x-axis. Reflection across x-axis because of that -2. So now, reflecting this across the x-axis, instead of being up here at 1, +2, I'm going to be at 1, -2. Instead of being at 2, 4, I'm going to be at 2, -4. So my graph is going to kind of flip around, and it'll have a negative slope now. And this is my graph just of step 3 now. For step 4, any vertical translation happens now. So any vertical translation based off of having a k value added after the function has been evaluated. So in this case, I add 3. after the graph has been, the function has been evaluated. So there will be a vertical shift of +3, or 3 units up. So vertical shift of 3 up. So what does that look like on the graph? Where I was at 0, 0, I'm now at 0, 3. Where I was at -1, 2, I'm now at -1, 5. So here I'm at 1, -2, and I'll add 3 to that, and that gives me a point here. So I'm going to have a downward slope here. And this is my step 4. So, and it's not just my step 4, it's my final graph. My final graph is at step 4. So overall, what transformations did I make here? I had a vertical stretch of 2. I have an x-axis reflection because of that negative sign. And then I have a vertical translation of 3 units up. And that summarizes all of the transformations that were made to get from the original parent function, f of x equals x, to this transform function, g of x. I hope this helped.